He's been my first student. When I started back in 2019, he joined my group. And in the past 6 years, he's been an amazing student. It was such a pleasure to work with him. He has achieved many, many great things in his 6-year career, including many papers, many awards, many honors. Basically, whatever award that we nominated him for, he got it. Beyond that, he's a wonderful person to work with. And I'm very happy that I'm standing here and introducing him on his final thesis defense. So with that, let's welcome Soroush on his defense, and let's listen to what he has to say to us.
So thank you, Professor, for the kind introduction. Hello, everyone, and thank you for joining my thesis presentation titled Reconfigurable and Interference-Tolerant Receivers for Next-Generation Wireless Systems. So we have Wi-Fi, Bluetooth, GPS, 5G, all packed within the sub-7 GHz spectrum, and 6G is expected to join soon. And our smartphones, we expect them to handle all these applications seamlessly, but delivering on that expectation involves a surprising amount of hardware complexity. So while these applications all fit within the same band, if you open your smartphone and take a look at the RF board, you probably see something like the picture on the left. You figure out that you have dedicated radios for each of these applications. And that's the first layer of complexity. If we zoom in one of these chips, you're probably gonna see the RFIC chip that's responsible for sending and receiving the data. But you can also see that there are many off-chip components accompanying to that to make this communication reliable. And having these many off-chip components is the second layer of complexity. And that doesn't stop there. If we zoom in more on this RFIC chip, we figure out that to cover the entire 7 GHz spectrum, we need multiple radios, each responsible for covering a portion of that frequency range. So now imagine a unified radio receiver design that could replace all these separate components that we taught so far, and we'd agree that it would dramatically reduce both cost and complexity. And this is the concept, the topic of my PhD research. And in this talk, I will go over the challenges that we need to address for this notion of all-in-one communication radio. And then I will walk you through these 3 main contributions from my PhD research, which each of them tries to bring us closer to the notion of multi-band, multimode radio. So perhaps the most straightforward way of implementing a reconfigurable receiver is to digitize the entire frequency band and then postpone all the filtering, amplification, and demodulation later in the digital domain. And thanks to the advancements of the CMOS technology, we can do efficient computation in the digital domain. And for any reason, if you want to change the frequency band that we want to select, we just need to change or flip some digital bits inside the software, and that would do the job for us. And we literally do not need to touch the hardware. The hardware is just a wire. And this was the vision Motorola had in 1995 called software radio. And in this radio, we probably only have one component, and we need to find the specifications for that. In real case scenarios, our desired signal is accompanied by noise and also blocker coming from our standard or other people using different standards in the same band. The level for the blocker we can expect is about 0 dBm. It's a typical number. And if we want to detect signals as close as noise floor, which in this case is going to be minus 100 dBm, then we would need 100 dB of signal to noise and distortion ratio. And then if you plot this here with the y-axis as the SNVR and the x-axis the frequency range that we want to digitize, in this scenario it's going to be 7 GHz. That star locates our desired ADC. However, if we thought all the available state-of-the-art eight to analog to digital converters, we will see that we have a clear distance from what's achievable today. And more importantly, it's not only not achievable today, it's expected to not be achievable in the future. And the reason behind it, if you put these numbers and use the famous figure of Mears for ADCs, that architecture is going to consume about 100 watts to kilowatts, which is clearly not reliable in smartphones. So we clearly need to do something about it. The first is that we need to do some filtering before the ADC to suppress the blockers in the environment. And we need to also do some frequency translation to lower the speed requirement of the ADC. And in the context of a reconfigurable receiver, achieving that filtering is a little bit tricky. The first thing about that filtering is that we need to achieve that bandpass filtering as early as possible, because in the modern CMOS technology with a typical supply voltage of 1 volt, that 0 dBm blocker that we talked about it earlier, if it receives only a gain of 2, that would clip to the VDD and saturate the entire receiver chain. So what do we have as options for this kind of filtering? The first thing we can do is that we can on-chip place LC tanks on-chip at different nodes of the receiver chain to protect the LNA, mixer, and what comes after from the interference. But the problem here is that we have limited programmability when we use the LC bandpass filtering. And as you can see here, the on-chip inductors also occupy a large silicon area. They have poor performance. The other option would be to use a pretty wideband amplifier and do all the filtering outside of the chip, which clearly that also defeats the purpose of having a reconfigurable chip and receiver that everything is integrated. So is there another option for doing this bandpass filtering? And the answer goes back to an idea from 1949, which is called N-pass filters. So if you take this low-pass filter, which consists of only a single resistance and capacitor, you can convert it to become a bandpass filter by splitting that capacitor into N parts and then sequentially connect those capacitors to the resistance that we had before using this non-overlapping clocks plotted here. And then if the clock frequency is FLO, then the center frequency of this realized filter is going to be FLO. And the only thing that we need to make sure, the condition that we need to make sure is correct is that the time constant of this filtering should be much larger than the time period of the clock. So the benefits that comes from this N-pass filtering is that it's fully reconfigurable. If you want to, tune the bandwidth, you just need to change the size of those capacitors. If you want to target another frequency band, what you need is just change the clock frequency, and the filtering follows. And moreover, if you take your output instead of that RF load from across the baseband, the voltage across the baseband capacitor, that naturally comes with a frequency translation that we wanted as well. And the way that this N-pass filter first introduced, those switches were implemented using mechanical switches, but thanks to the advancements of the CMOS, we now have available switches that can operate at gigahertz rate. And because of that, this N-pass structure found its way into very modern CMOS wireless technologies like LTA first or the mixer first design. And you can see that these blocker tolerant receivers are reported to have a bandwidth, a tuning range from 1 gigahertz up to 10 gigahertz. So sounds promising, but there is a severe caveat inside this N-pass filtering. So the good thing about it is that bandpass filtering, which is around the desired clock frequency, that's good. But the problem here is that also comes with multiple passbands around harmonics of the clock frequency. And why is it challenging? The reason behind it is that there are many practical scenarios that you can find that a blocker falls exactly at those harmonics of a receive band. For example, in 5G standard, a user transmitting in N79 band could be an interferer for other users receiving signals in N8 or N40 bands. So if I use that M-path filter as my filtering block in my receiver, let's say in a mixer first design, those blockers will not receive enough attenuation at the RF port. And because I'm mixing with square wave LOs, then all of those blockers will down convert to the baseband because this square wave LO has multiple harmonics. And so we need to somehow eliminate these harmonic contents, and our particular interests are the third and fifth harmonic that are the most challenging one. We need to attack them as soon as possible. So the idea of harmonic rejection has been around in the community as around, even in the power electronics domain. But the core concept in the core concept here is that we need to figure out apply filtering to these square wave LOs to imitate a pure sinusoid wave. And in context of an 8-path filter, that would mean that we need to apply a 3-tap FIR filter with magnitudes of 1, square root of 2, and 1. And that way.
So can you give me an intuitive reason why the odd order harmonics would not be filtered by a normal M-path filter?
So I have an explanation later on. If you,
okay,
yeah. So I have a slides for that intuition behind it. But the cool thing is that the odd harmonics that we have here, each time that capacitor connects to the antenna, let's say, it sees the exact same portion of the waveform of the signal, and it continuously charge up on that, and that causes us to see this large signals at our input. But I have some slides later on that can explain it further. So now that we know that we have this technique, let's see how can we implement it in a circuit design. So we can use weighted active amplifiers to sense the voltages across those baseband capacitors, and then combine them in a way to create a new baseband output that's free from harmonic down conversion. And no matter, so this technique can be applied right before the ADC at even earlier stage using a multi-input, multi-output harmonic rejection TIAs, or even in the RF domain. But nevertheless, you will always find an active amplifier that sees these blockers at its input, or even worse, an amplified version of it at its output. So the scope of harmonic rejection achievable through this active harmonic rejection is only limited to small signals. And if in pursuit of having the ultimate linearity with respect to these blockers, the question arises, is it possible to modify this N-path structure using only passive components? So we forfeit the use of any active devices so that we get higher linearity. But the moment that we see the passive board, that should cause an alert that because of that passivity, we're going to see some loss, and we need to innovate some new techniques to address that loss. And that's going to be the topic of my first project here. So if you want to address this, add another sort of filtering to our M-path filter, the techniques that we have are either charge sharing, which means that we pre-charge capacitors and put them in parallel later on, or having pre-charged capacitors to stack on top of each other. And let's see if we can achieve this harmonic rejection using each individual of these techniques. So we can explore charge sharing as shown here. We have 3 capacitors, and now they are weighted with 1 square root of 2 and 1. And the moment they're pre-charged, after that, we can connect them together. And as you can see here, the effective LO right now is going to have no third or fifth harmonics. The problem here is that because we have multiple charge sharing events happening in this circuit, we get 15 dB of loss in the typical scenarios, which means that we cannot use this kind of a structure without an active buffer feeding it. So capacitor stacking is another way to incorporate an FIR filter within the switch capacitor circuit. And this method can lead to passive voltage gain because as you increase the number of stacked capacitors, the voltage increases. And the challenge here is that the FIR filter that we are looking for at taps of 1, square root of 2, and 1. And this time, what we see here is that the second tap is 1. And the way we cannot do much about it by changing the size of the capacitors because the Thevenin voltage here doesn't depend on the size of those capacitors. And we need to approximate. And even with the simplest approximation of square root of 2 with the rational ratio of 3/2, we'll see that we end up with a structure here that has 7, the number of the capacitors are 7 per path, the number of switches per path is also 20. So it's a pretty complex design. And because that we use that approximation also is not give us perfect harmonic projection. So there is a trade-off between the circuit complexity and harmonic projection performance. So combining charge sharing and capacitor stacking can potentially lead to a better hybrid solution that leverages the strengths of each of these methods while minimizing their weaknesses. And there's a proposed circuit for a fully passive design is shown on the right. And going on, I will explain step by step how the circuit operates. So similar to other previous techniques, we need to pre-charge some capacitors and then connect them together. And that happens here that we have 3 capacitors and they are pre-charged through phi 0, phi 1, and phi 2. And then when the readout phase, the phi 3 comes, the 2 stacked capacitors on the bottom path are going to be becoming parallel with the top one capacitor labeled C sub B. So the capacitor stacking is responsible for realizing the first and the second, then the third tap of the filter. And by properly selecting the size of the CA over CB ratio, the charge sharing will realize the second filter tap that we were looking for. So this gives us the LO shaping FIR filter that we are looking for, but to be a practical system, we also need to make sure that the loss of the system when it's not accompanied by any active buffers is also manageable. And we can see if we compare this design with the previous only charge sharing method, we'll see that not only the loss is much smaller, but also as we try to increase the size of the capacitor to get to generate higher Q filters, the increase in the loss is much more gradual. And this can be explained intuitively that the proposed architecture has fewer number of charge sharing events, and we have capacitor stacking with some sort of passive gain that somehow offsets the partial loss due to charge sharing. So this is a promising architecture, and if we just convert it to a differential design, as shown here, and put it in a mixer first receiver architecture, we'll end up with the first system block diagram shown here. The design is followed by baseband LNA for amplification and another recombination stage in the baseband domain. The design was fabricated in the 45 nanometer SOI technology and occupies a silicon area of 0.65 millimeters squared. The measurement result shows that this design can be controlled over a wide frequency range from 250 megahertz up to 2.5 gigahertz with a gain of 35 dB, and it's matched across the entire band. The most important metric about this system is that we now are able to attain more than 40 times harmonic blocker tolerance compared to the state-of-the-art broadband harmonic projection receivers. And this is thanks to the fact that we didn't use any active element inside our mixer structure. And so far, what we achieved is something like this. We have a mixer or an path filter that there effective LO, it exactly looks like 1 square root of 2 and 1. So there is no harmonic down conversion from RF port to baseband domain. So any baseband amplifier that follows this mixer is immune and protected from those blockers. Something that we didn't answer is that still at the RF port, we see those harmonic peaks, and we don't, attenuate those harmonics at the RF port. And the question is that can we do better? And this is the topic of the second project. And to answer that question, we need to go one step back, which is going to be the answer to your question. Why do we see those harmonic peaking inside our structure? So here we have applied a 3-FLO blocker to an 8-path filter, and we're going to track the response to it for the voltage across one of these capacitors, for example. Starting from a 0 initial condition, this capacitor starts, when phi 1 activates, it starts charging up, but because the time constant is not, it's very high, so the filter doesn't settle. And as a result, the capacitor only charges onto this partial level. And the voltage remains across the capacitor until the next cycle that phi 1 activates. And because the blocker frequency is exactly 3 times the LO, the capacitor samples the same part of the waveform each cycle. And as a result, each cycle, it continues charging and building up voltage step by step. And at steady state, we get this high value. And if I stitch these high value, the capacitor voltages from different paths together, I will get the voltage response at the RF node, VRF, which is this step-shape waveform, which has high swing. And if I take the FFT for it, that would be the reason behind that I see this strong peak near 3-FLO. For other frequencies that are not an integer multiplier of this clock, each time that the switch connects, the capacitor sees a different part of the blocker signal, and as a result, some sort of averaging happens, and there is an attenuation for that. So the key observation here is that we need to somehow avoid this non-interruptible charge buildup across these capacitors. And one way that we can do it is that the moment that switch phi 1 opens, we just reset all that capacitor to ground. And by that way, we always interrupting the charge buildup across these capacitors. And the voltages that is stored on these capacitors is going to be limited to some very small number. And then if I put those voltages from different capacitors, put them together, then definitely I'm going to see a smaller voltage swing at the RF node. However, this is an impractical implementation. Why? Because it's good in reducing the peaks around the harmonics, but it's also going to reduce the peak around the fundamental frequency. So that nice bandpass filtering that we had is going to fade away. If you think about it, this is just the resistance that we implemented. And because the size of the capacitor is also large, the size of that resistance is very small. So ideally, we want to have such a circuit that does the job of resetting for harmonics. So we need a circuit to provide a short at the terminal of phi 2 when it senses the harmonics. But we want a circuit to provide an open circuit when it senses a fundamental frequency, which is our desired signal. And think about it, at first glance, this seems a complex thing. Perhaps we need transmission lines to differentiate between the harmonics, similar to something that happens in power amplifiers, class F matching, or a complex analog and digital sensors to implement such a circuit. But remarkably, it takes only just one switch and an extra switch and a capacitor to realize this reset mechanism. And while the circuit seems to be very simple. The underlying math is quite involved, and I won't go into the details, but I will provide some simulation results to convince you that the circuit works. If I compare the proposed harmonic rejection mixer's harmonic profile with the conventional structure, I see two things. The first one is that still the design is low loss around the fundamental, which is good, and I see that bandpass filtering around the fundamental frequency. And more importantly, I see more than 20 dBs of harmonic rejection for the second, third, and fifth harmonics. And that's the key feature of this design. When it used in mixer first designs, it will gonna give you harmonic rejection right at the antenna interface. And the circuit to operate doesn't need to have any relationships between CA and CB. You get this harmonic response at its input driving point. But if we select this ratio of CA over CB wisely, then we can get an added bonus. The LO waveform of this entire system is gonna also go over through a FIR filter to eliminate the third and fifth harmonic. So no remaining harmonic blockers at the input RF port will translate to the baseband. So to illustrate that more, I here apply the 0 dBm signal to both the conventional 8-path mixer and the proposed harmonic rejection mixer. As you can see clearly, the voltage at the RF node of the proposed design, that blue trace, is much smaller than the red trace. And because we selected that ratio, then any kind of remaining blockers, when it reaches across the capacitor CA, it's gonna fade away. And if you think this plot is exactly that harmonic reset switching that we were expected to happen. And the cool thing about this design is that no matter if your N-path structure or passive mixer using your receiver is it in single-ended form or differential, you just need to add some switches and capacitor to it as a harmonic rejection extension to boost the blocker tolerance of that design. Here, this slide shows the system block diagram for the next this project, and in which we opted for this new differential passive mixer, and we replaced it with the one that we had before, and the rest of the system remains the same. This design was taped out in 45 nanometer SOI technology and occupies a silicon area of 0.68 millimeters squared. This time, because we've used fewer number of switches, we are able to extend the frequency operation up to 4 gigahertz, and we can get matching across the entire band. The noise figure of system, again, because we have fewer number of transistors, the noise figure of the system is smaller. Starts from 2.6 dB for low frequencies up to 5.5 dB. And when I excite this device under test at its input with blocker signals located at harmonics, you see that it can tolerate 14 dBm and 16.5 dBm of power, respectively, for the third and fifth harmonics before the system gains drops by 1 dB. And this is amazing because it's now 2.5 times higher than the architecture that we showed earlier, and 100 times higher blocker tolerance compared to the active harmonic rejection methods. And this is thanks to the fact that we are doing passively as early as possible harmonic rejection in the receiver design. And that brings us to the last project, which is an example of how versatile this technique can be. So traditionally, IoT devices operate on fixed frequency bands. And the main focus when designing those, for example, in BLA standard or Zigbee standard, is to lower the battery consumption as much as possible and lower the implementation costs. But with the new IoT use cases, like wearable healthcare, smart cameras, industrial sensors, the 5G standard now opens up a multi-gigahertz spectrum access for IoT deployment. And now we need to also think about reconfigurability when we're talking about IoT. So this N-path filter proves to be very useful when it comes to reconfiguring the receiver design. So let's see if we can use it in here in the IoT application as well. So the challenging thing about the IoT application is that when you want to go more to narrower bands, like 5 megahertz and below, the area that you require for this bandwidth that this N-path structure generates for you is going to be huge. You're going to need the 1 nanofarad total capacitor on chip. And to have a decent amount of rejection, out of band rejection, you need to size your switch to keep a switch resistance of 10 ohm, which then requires lots of high power consumption, dynamic power consumption. One way to reduce both the area and power of N-path filtering is to place it across a negative gain and leverage the Miller effect. And instead of both the size and the dynamic power are reduced by the amplifier's gain, which makes it very interesting for IoT application. But again, if we plot this profile of the transfer function V over ES, we're going to see that those we see that the LNA is not protected from the harmonics. And the only way to protect this LNA from the harmonic blockers in this design is to somehow modify the driving point input impedance of this N-path design. And if you think about it, in previous design where we added the harmonic rejection extension to this N-path design, we somehow modified its input impedance. And we can, in a simple model, we can think of it as a parallel combination of a regular N-path with a resistance which its value is frequency dependent. That resistance REQ shows its high values around the fundamental frequency and low small values around the other harmonics. And that way, if I make them in parallel, the actual input impedance only peaks around the fundamental frequency, which is exactly the circuit that I needed to put across that amplifier. And when we place the circuit across the amplifier, not only we achieve the sharp filtering, but also we get suppressing of harmonic blockers at the input of the amplifier and also the output of the amplifier. And you can see that more than 25 dB of third harmonic rejection is achieved here. And despite this design being a single-ended design, it's effective for both odd and even harmonics. And then this architecture looks promising, but there are a couple of questions to be answered. For example, how are we going to extract the baseband voltage here in an efficient way? So presumably we need some sort of switch capacitor interface to extract that voltage, boost the signal further to reduce the power consumption demand on the baseband amplifier. And also, since we are designing for IoT applications, we want to operate on a very small power supply, let's say 0.6 volts, and then running those switches on and off, turning those switches on and off is going to be a challenging issue. And we needed to come up with a clock boosting technique that's both low power and area efficient, because again, we're talking about IoT. And I'm not going to go inside those techniques because for the sake of time, but when you apply those techniques, the system block diagram looks like this. And in this design, if I just go ahead and remove that switch by 1 in the feedback path, which to break the harmonic reset switching and then make the design to be exactly the conventional gain boosted design, the blocker tolerance for the third harmonic is then reduced from -3 dBm to -18 dBm. And that's a 15 dB of difference, which shows the effectiveness of this technique. This time, we didn't have access to the 45 nanometer technology. We needed to figure out the way to take out the 22 nanometer technology, which is a very painful task. And the silicon area occupied here is 0.048 millimeters squared. And to put it in context, this is the area that our previous chip occupied, and you can, as you can see, you can place 15 of these new chips within the same area, while also achieving a 10x improvement in the lowering the power consumption, and also achieving a narrower bandwidth. Of course, we didn't go for crazy for the harmonic blocker tolerance, but this serves best for the IoT. And the measurement results show that the architecture can be tuned across a wide frequency range up to 3 gigahertz, and with a decent noise figure of 3.7 up to 5.3 dB across the LS. So to conclude, we saw that why we need reconfigurable designs, because that's going to be a very hardware efficient approach. We saw that N-path filters play a significant role in that, but they have some problems, and we tackled that harmonic blocker issue of the N-path filters, which is to be a considered to be a fundamental issue. I mean, since the advent of the N-path structure. And we boosted the harmonic blocker tolerance by 100 times. In our design, you only need to use switches and capacitors, so it benefits from technology scaling. And it's a versatile technique. And if you to highlight and emphasize this phrase as versatile technique, I have some slides about possible future work. So the N-path filtering that we get from the filtering response that we get out of this structured N-path design is has a second order roll-off. And in many applications like Wi-Fi 7, that your channel bandwidth should be about 160 megahertz or 320 megahertz, that's not enough. And we probably need a bandpass filter with wider bandwidth, sharper and steeper roll-off. And there are techniques based on this N-path design, this N-path filter, to synthesize those sharper filtering. One of them, which I'm showing here, is that it couples 3 of these N-path designs by using gyrators. And my point is not to go over how the circuit operates, but just to provide this simulation for you that it gives much wider bandwidth around the LO frequency, but still it has the issues around the harmonics. And perhaps the simplest way to get both the wider bandwidth, steeper roll-off, and get rid of those harmonic responses is to just replace those N-path designs that you have with this new setup. And this is not, I'm not saying that this is the most optimum design, but this is just the first try that you can, simulate in 5 minutes and see that it works. So before I conclude my talk, I need to acknowledge a lot of people.